So, to start the tour today, we'd like to just do these two side-by-side comparison of persons. These are 8 foot by 8 foot rooms, so relatively small room, but not that out of the ordinary for a small room for a relatively small apartment complex. The fuel load, as you can see in there, is relatively small, particularly those of you who might have small children like myself. There would be about 200 pounds worth of additional stuff in there, right? All the plastic, and it's all plastic, right? It's not the wood blocks anymore, it's all plastic toys. When we talk about the amount of potential energy that is stored in modern combustibles, the typical rule of thumb is we have about 3 times more energy per pound of fuel in our houses. Now we think about how much more stuff we have in our house. So, a gentleman was talking about a furniture store fire 40 years ago. Compare that to what happened in South Carolina about 10 years ago, where everything was polyurethane foam, and how quickly that went up and how rapidly that fire developed. If you're interested in really looking at a comparison between fuels from modern versus legacy, in legacy we talk about fuels from about the 1970s or so. What were most couches made out of in the 1970s? Or before? Any ideas? Before that. More recent one, almost everything we have now is foam rubber. But in the old days, it was a lot of cotton, wood, a lot of natural materials. Everything we have now, some people will say they've got basically solid gasoline in their apartments. Basically, your couch it's a hydrocarbon. It comes from liquid hydrocarbons. It has a very similar amount of energy per pound. So we'll see how little fuel in here, how quickly it takes for that fire to develop to that transition, which Chief DeLuca mentioned was called flashover. At which point, nothing can survive. Firefighters can't survive. The gear will only withstand that for a number of seconds before it is completely destroyed, and the firefighter inside that cannot survive any time at all. So I think we're ready to light off. We can find our arsonist. Ready to go? Arson investigators happen to be some of the best fire setters in the world. So we're going to start off with the burn cell that we have on the left here, facing it on the left. Very lightly fueled. Okay, there's just this one couch in here. The couch has polyurethane foam. There's no accelerants that are being used in here. This is not an accelerated fire. Eddie is going to ignite in the wastebasket down there at the bottom, just some crumpled up newspaper.
Remember that premise, big fire starts small? That's a relatively small fire, easily extinguished by a fire extinguisher, right? If you don't get the fire extinguisher quick enough, why we require them in commercial buildings, that's going to grow into something big relatively quick.
What are you hearing? Now we're 20 seconds into the fire. What do you hear? Smoke detector. Can you control that fire with an extinguisher?
Yeah.
Bottled water, possibly. Or at least can you get everyone in your family out to safety and call the fire department? One of the reasons we're seeing fire deaths go down so drastically is because of systems like this, as well as the sprinklers that we'll talk about in a little bit. Those of you who haven't seen it, this is the timer here. So we're at 43 seconds. If you want to get an idea of how this fire develops, this is your timeline right here. Look at the color of the smoke. The one thing that we tell firefighters is smoke is fuel. All of those black particles, this is a much darker, thicker colored smoke than we would see from traditional materials that burn much more clean. All of that soot in there is flammable. We also have wind going this direction. Those of you who don't want to smell like smoke might want to move over a little bit to the left.
Hey, you know how we can tell us the wind's blowing that direction? Because the smoke's going that way, right? Very technical stuff.
All right, so the flames have now spread up to the ceiling. The fire needs obviously 3 things. It needs fuel, it needs heat, and it needs air. As the flames start to develop and the smoke layer breaks back down, instead of the fire getting good air that has 21% oxygen, it starts recycling some of that dirty air that's already been used. It has less oxygen in it. So just like those of you might have worked on old carbureted cars, when they're fuel rich, they start belching out more black smoke. You don't have them carbureted, you don't have the air to fuel mixture properly fixed, it burns less efficiently. The fire is spreading across this couch now due to radiant flame spread. You can see it in the bottom there, look at the black smoke billowing out. That black smoke is re-radiating heat back down. We're now 2 minutes into the fire.
Look what's happening now up high in there, right? Don't look at the base of the fire, look up high. That fire is growing up at the superheated gases up high in the space.
We're now nearing flashover. We've got flames issuing out. Look down at the carpet on the bottom. You see all that off-gassing? That is getting ready to ignite because it is transitioning from solid to a gas. And as we continue, unfortunately our soffit's melted off with it, which doesn't help hold it in nearly as much. But we've transitioned from a fire in a room to a room that's on fire. Floor to ceiling, wall to wall, we have gone to flash over. And 2 minutes and 45 seconds. Okay, Dan, go ahead. 2 minutes and 45 seconds. With that very small fuel package, we transition to flashover. A couple things to remember here. Not much fuel. The other thing to remember is ventilation. This is one thing, particularly you as designers of buildings, one way you can determine about flame spread and how fires transitions from one room to the other is the amount of pathway that you provide, the amount of ventilation you provide for that fire. If we had a door closing this off, all that smoke would just bank right back down. The fire might actually smother itself. We would significantly restrict the amount of extension from that fire by compartmentation. What are modern homes? How many people want to have small rooms in their homes? If you're building a residential house, who says, "Oh, I want a bunch of 8x8 rooms with doors in them"? Anyone ask for that? You want open plans, right? You want the great rooms. You want the McMansions. It's got the 20-foot ceilings that you can see from one end to the other and 50-foot open spans. And that allows fire to spread. That allows the fire to get all the oxygen that it wants, just like we had right here. So that's one way in which architecture strongly influences the way fires develop. In addition to the stuff that we have, you're not going to change the stuff that we have. People are going to keep buying plastic, keep buying foam furniture.
What's missing from the burn cell that's not in there that would normally be in a home? All the wall coverings. If it was a commercial application, we'd have all that really cool wall covering on there, you know, the Class C flame spread stuff that really doesn't stop fire a whole lot. That's not even in play. Plus, what about window treatments? Right? Where's that heat go? The heat goes up, what does it do? It captures the window treatments, lights them on fire, drops them down, we get a drop down fire. So now if we had a fire on this side of the room, which is cooking very well by itself, we now have a drop down fire on the other side, which is what? A second point of origin. Perfect. This room is going to, and then once it gets to that point where it flashes over, everything up high says, I give. And that's what you saw right at the end. The smoke banked down, got to about here, stay low and go, right? Because the heat and smoke are up high, so we're going out. Firefighters, why do we advance on our knees? Because the heat and smoke are up high. It's the same stuff, right? We're going in, you're coming out. Once that heat layer got down far enough, the walls just went like that. And what are the wall finishes? There's nothing really combustible about them, but you saw the walls were on fire. That's the point when the space itself flashes over. Everything in that room says, Uncle, I'm going to let go. And that's the point where if we sense a flashover as firefighters, we have to back out. The one reason that the fire went out very quickly is we're throwing 150 gallons a minute off of a fire hose, right? So we can do that. That portable fire extinguisher, when that fire was rolling,
This one's set at 30.
oh, I'm sorry. Thank you. Okay. No, I'm not going to do it. All right. So a fire extinguisher obviously is going to, yeah, it's going to slow things down, but at some point you have to know when to say when, right? This fire is way too big. That's why we had a conversation before the seminar, why are the fire extinguisher cabinets always an issue? Why are these goofy red extinguishers always located in the really nice lobby that we designed? Because they need to be on the means of egress out of the space. We don't want people to run in to get the extinguisher to turn around and be trapped. We want the occupants to run to the door, stop, make a conscious decision. I'm trained in the use of the extinguisher. They've put one here for me to use. I'm going to go ahead and I'm going to advance back on this fire because I think I can do it. So that's why those extinguishers are always in the way. Can you paint the extinguishers to match the wall? Yeah, you could, but no one would see them. Could you put them in a fire extinguisher cabinet so they're hidden? Sure you can. So what do fire code officials require? A three-dimensional sign on the wall above it now because the whole purpose that they're painted red is so you can see them. I'm done.
How do I follow that?
Yeah.
All right. So, a couple things. I hope that many of you, at least those of you over here, what did you feel? Heat, right? So that's the other way that we can help protect some of these buildings, right, from a fire protection standpoint. A lot of cases, sprinklers have difficulty working in really, for example, very tall atriums where the smoke may not have enough buoyancy to get all the way up there and trip those sprinklers. There's different ways that you can protect some of these occupancies. One of the main ways that fires spread is by radiation. So if you were hot enough standing close enough to that, there's enough radiant heat, you would ignite. So one way that you can help protect things is by moving the different fuel packages to different distances, particularly in areas that are difficult to protect through sprinklers. This is the other reason why a lot of those large atriums, you can't have too much stuff in one area, otherwise that fire can spread from that initial package to the next, till it gets big enough that then it can really involve the structure. Right? So there's more than one way to fight the same type of fire, more than one way to skin that cat. One very effective way we're going to show you right here. Remember that timeline, 2 minutes and 45 seconds. That was the flashover. Anyone that would be in that room intimate with that fire would have expired long before that. Probably within that first minute. Those gases, that heat would have been too much for an unprotected individual to survive. Even with our gear, with our response times, we've got less than 3 minutes for a fire like that. The firefighters who are watching, how often are we going to get by the time the fire has started to the time we get there? Maybe some of you might be able to get there in my volunteer department. 4 to 5 minutes, 5 minutes. So realize how important it is that you have that timeline. So if you go back to your families, to your coworkers, this is a timeline that we're dealing with now. In the old modern furniture, or the legacy furnishings, Underwriter Labs up in Northbrook has done a lot of great research on this. And they've shown a very similar fuel package back in the day with the wood, the natural materials. It takes about 25 to 30 minutes to flash over. That's what we used to have, that's what we used to respond to 20, 30 years ago, versus 2.5 minutes to flash over. And that's also the importance of the smoke detectors and the sprinklers, on warning you to get out. Even if the sprinkler can just control it, maybe not put it out, it gives you and anyone else in your house or your place of work time to get back out. All right, Eddie, we ready to light off the next one? Okay, so basically identical fuel packages. Oh, sorry, go ahead.
How thick was it? What happened to it over there in the corner?
These actually are not lined with gypsum. These are lined with painted OSB.
That one is gypsum.
That one was gypsum? Okay. Yeah, it was gypsum. Are you asking about what happened to the...
Yeah, what happened to the edge?
Well, we had a plexiglass soffit at the top there. So that melted down. That might be what... We can take a look at it afterwards if you want.
And that's what we had across the header.
Oh, I saw that.
Yeah. I think that's what you're seeing off to the side there. Yeah. Right. Yeah. Sorry, that was gypsum on that one. Okay, so we have basically the same burn cell, almost identical fuel package in the fire sprinkler protected burn cell right next to it. So Eddie will light in the exact same location. We'll start the timeline. Actually, we got about a 5-second head start on that time. So we're about 5 seconds advanced there from the time. You should see the fire basically develop the same way. Then about 10 seconds, the smoke detector goes off.
Yes, sir. Yeah, we all checked it.
Okay. Notice also on the edge of that, the coffee table there, we have that fabric softener bottle. That never caught fire. This is what that fabric softener bottle looked like. At 40 seconds, what has occurred? Sprinkler. So the sprinkler has controlled the fire. We can continue letting this go. The sprinkler, at this point, the fire is small enough. The sprinkler will eventually put it out. But just to conserve some water, we'll go ahead and do suppression. You can see how this sprinkler has limited the damage within that room. Notice that fire did not grow as soon as that sprinkler let go. And it kept the fire into that one small area, reducing the amount of smoke that was given off, which, by the way, is what kills most people in fire. It's not the heat, it's not the flame, most people end up dying as a result of the smoke inhalation from that fire. 40 seconds in. We've got a little bit of damage to the edge of that couch. No real damage to the coffee table. Definitely no damage to our fabric softener bottle, which could be representative of anyone that might be in that room. This is the type of radiant heat that you would be facing. Skin gets damaged much lower temperatures than fabric softener bottles do.
So you probably don't need to ask me what my opinion of fire sprinklers is, do you? If you did, and maybe today's demonstration might bring it to light, there's been a huge discussion at the national level to entertain fire sprinklers not only in commercial buildings but also in residential buildings, right? We won the commercial building fight, and in this case here, this is a residential fire sprinkler head. So, as Gavin was pointing out, it really never suppressed the fire. Fire sprinklers don't suppress. Fire sprinklers control the fire long enough so the fire department can get there and put a good hit on it and save lives and property. In the residential application, we talked about trying to get fire sprinklers in residential applications. We had a lot of discussions about it at the national level, the architects, the fire protection consultants. We got it in the code, but then we got it pulled out of the codes, and it was in the codes and it was out of the codes, right? This is the difference. Your house will burn down if it's unattended by the fire department, or if you have fire sprinklers, it's going to control the fire, and this is a key point with residential fire sprinklers. It will control the fire long enough to safely get out. In residential applications, the fire sprinkler system is not designed with the capacity that we have in commercial ones. Residential, control it, get my family out, get the fire department in, the fire will be extinguished. In a commercial application, we're talking about fire areas of 1,500 square foot. We're talking about minimum GPM flow out of the fire sprinkler system. Commercial applications, it's designed to quell that fire throughout the entire building, whereas in this case, quell it in the room it started in, get everybody out. That's why you don't necessarily see fire sprinklers in all rooms in residential design. Some of the codes exclude them in bathrooms, some exclude them in closets. Once again, it's find the fire, extinguish or control it, and protect the means of egress out to either the front or back door in the house. Okay? Huge difference in timing, huge difference in property loss in this scenario.
So Chief, how much would a typical fire sprinkler system cost in a newly constructed building?
Well, we've heard discussions anywhere from 10 to 15,000 in a residential application, right? So you got to do the math. I mean, if you're depending on the size of the house, locally for us, the city that we're working within wrote an ordinance that says any renovation over 50% in the area, mandatory fire sprinklers. So what did all the residents do? Complained because now you just added 10 or 15,000 to the cost of potentially what, a 50,000 square foot room addition off the back, right? So politically that got quelled pretty easy. On the commercial side, we kind of take that math off the table. You know what, if you have enough finances to build a building, to renovate a space, to lease a space, you can accommodate the initial, or not even the initial cost, you can accommodate the renovation cost of moving some sprinkler heads around. I think we've all probably seen commercial space, more often than not the fire sprinkler system's already there. It's a matter of moving those heads around to get the coverage, right? So the cost is minimal in commercial applications once the system's installed.
So there's a big push, obviously, throughout the country for this green buildings, right? So that we have things that are environmentally friendly. There's a discussion in the fire service about, can we make a push also for safe buildings? Is there a premium that can be paid on designing and building safe buildings as well as energy efficient buildings? And how can the two come together? There's a lot of things that are going into our structures now. This is just one example. But there's a lot for, say, some of the green initiatives that are really changing the way we have to respond to fires in the fire service. Solar panels on the roof significantly change what we have to do to respond, because you have 600 volts sitting on the roof that doesn't turn off. Even with the sun out, depending on what kind of tarp you have, it might go right through the tarp. Depending on what kind of lights we have on our apparatus, might start that solar panel. Cars that are plugged into the building. In many cases, these cars can backfeed now, right? So you think you've pulled the meter out front and killed all the power inside the structure. Well, now we have a battery in a car that can feed back in and still keep things active. So there's a lot of things. You guys are at the forefront of these new developments coming into buildings, coming into not only the commercial structures but the residential structures. And on the fire service side, we're trying to understand how can we respond to those? How can we develop safety measures such as this? So when we send someone up to the roof, they don't get nailed with 600 volts. When we think we've taken care of the power, we don't recharge something while we're in there operating on it. Okay. This is actually a really exciting time for all of us because of all these things that are coming out, because of all these new developments. But hopefully what we're able to provide with you is just a little bit of a demonstration of how these things affect us in the fire service. And as we take a tour for the rest of the hour here, any questions you might have about things you've seen, new designs, structural insulated panels, for instance, are coming into our buildings. How does that affect the way that fire is compartmentalized, and how does that affect the way the structure survives as a result of fire? When you're dealing with a structure that's really largely styrofoam panels, how much structural stability does that have under fire conditions? Because your building's under attack under fire, and yet we have to go in, and we might have to get a family member out, or we might have to try to save that structure. So we need to be able to work together, not just with the engineers, but also with the architects from a fire service perspective.
Real quick, what I found in the last project that I'm working on the last couple of years is that I'm in a 30-story high-rise downtown, and we're finding that the sprinklers are actually providing a false sense of security because they were installed in the 80s, and what was found out that a bunch of the heads, maybe 4,000, were recalled back in the day because they had a rubber O-ring. So we started going ahead and working for the client that we're working for, replacing, draining down, replacing these heads with non-recalled heads, of course. When we started taking down these heads, were the water sitting in there for so long, and something within the water caused a crystallization within the head itself. So when we hooked up that head to so much pressure and we broke the bulb, we weren't getting any water flow at all. So this is causing a huge concern that they haven't been necessarily flushing the system.
Right. Yep.
Because they can't flush the system, they're worried about leaks. And it goes on and on.
Yep,
So
exactly. Yep.
Yeah.
Good point.
Just like any other system, maintenance inspections are required, just like any other building system that might be installed. And if it's not maintained, it's not properly upkept, it can't be expected to work as it was designed to work. So, I mean, unfortunately, that's not a completely uncommon finding, what you guys are dealing with right there. But it also speaks to the importance of what's the value of the safety of that building. Does a building owner, how do they value that, and are they making that commitment?
Right.
Right. So,
One other point to make, for those of you who were kind of over here when we first started the fire in the uncontrolled room, right? You felt that heat kind of pushing out, right? You saw that heat kind of banking down, right? On the fire side, that's one of the reasons that we'll send our second or third crew in to the roof, right? We call it ventilation. What are we doing? We're giving that heat and smoke a chance to get out. Everybody sees that and says, oh no, the fire department's here, right? They're going to cut a hole in my roof. Yeah, because you know what? We can't gain access to that space. So we were standing back here, and I think we were all feeling the heat. We can't gain access to that space until we provide an outlet for that heat to get out, right? Heat rises, highest point in the structure. Well, typically a truck company goes up to the roof. You hear the chainsaws going. Got to cut a hole in that roof. And we want to cut that hole where? Above the fire or somewhere else? If I cut a hole here and the fire's where Gavin's standing, where am I going to draw that fire? To where I cut the hole, right? So we want to find the seeds of the fire, cut a hole in the roof. The next thing we do, you'll see exterior crews do outside ventilation, right? Fancy term, break some windows. What do we have to do? We have to let the heat come out. But here's the trick. The double-edged sword is break the windows, right? Let the heat out. What are we letting in? Right? Fire triangle. Heat, fuel, and oxygen, right? So the fire starts to starve itself. And then we break out the windows to let oxygen in, right? Kind of a bad thing. So what are we going to do before we open up those windows or that roof? We're going to have one of these hose lines right at the front door. When that hose line is ready to advance and ready to go fight the fire, we're going to say, you know what? We're going to let you get out. We're going to give you a little air, but the second we give you that air, we're going to get a hose line on you right out of the box. So when you see the fire department there, all the windows are coming out. Its reality is we can't go in until we get that heat level down. Ceiling temperature is 2,000 degrees. It's not going to work for us. We got to get that temperature down. A lot of times you see a fire may actually smother itself, right? It sucks all the oxygen out of the space. It starts to darken down. It's really thick and chalky. It's dark in there, right? You can't see anything. There's a fire in there. Everything is screaming, right? What do? We get there. We don't pop the windows because we know better, right? We don't want to provide air to that environment. We open that door, right? That room is screaming for some nice, cool oxygen to flare that thing up, right? We open the door, we feel a draft from our backside. The draft goes in because the space is right, it's expanded, hits that fire goes from a smoldering, non-existent fire to a flashover instantaneously. You've heard the term backdraft, you've seen the movie Backdraft, right? I felt the draft come from my back. That's usually a sign for us. You go, whoosh, and in about 3 seconds it's going to flare up and it's going to push that fire back out the window. So there's a lot of technology involved in how we put out these fires. It's not like the good old days, just throw some water on it and we'll be fine. There's a lot of science behind how we do this. And then that fire triangle, right, heat, fuel, and oxygen, yeah, the scientists got involved, right? They took a triangle and turned it into this 4-sided pyramid called the fire tetrahedron because they figured out that there's some chemical reaction that occurs now. That the piece of wood goes from a solid to a liquid to a gas. And there's a chemical that we can spray on that to stop that reaction. So what was simple now became complicated. But that's the stuff we're dealing with. The number one way we put out fires, you got to eliminate one of those 3 sides. And historically, the fire has gone out for us.
What Chief just mentioned is what we call a coordinated attack. So it's just like, my son started playing hockey, and I have no idea about hockey. I watch it, and it looks like people are just randomly going all over the place. Yeah. But there's plays, there's patterns. The same thing happens in the fire service, just like any other sport. It may look like people are independently going around and doing all these things, but if they're not closely coordinated, if we don't have that hose line ready when we make that ventilation opening, we don't have everyone in their right place at the right time, that's when things start to go wrong. That's when that ventilation allows that fire to take hold before we have a chance to cool it down. So this is why, when you see what we'll go through in the rest of the tour here, why we actually take people from individual task levels. From the initial academy, when they come here and just learn how to pull a hose, learn how to throw a ladder, from those very basics up to a 40-hour course where people are really looking at how to work on that same sheet of music. So everyone is going to that, following that same playbook, and everyone is doing this coordinated attack because you see how fast these fires are developing on us now. That playbook has to be faster, just like all the offenses in the NFL, any football fans, how fast everyone's moving. The same thing happening in the fire service. We have to be able to respond, we have to be able to adapt, and we have to be able to identify much more rapidly than what was required 20, 30 years ago. So that's what we're going to take you on the rest of this tour here to show you around. If there's any other questions actually before we move on?
If you want to walk up closer on the way by, take a closer look. We're not going to get into detail on fire investigation. We all saw where the fire started, right? So, I know where it started. But if you look closely, you'll see burn markings on the sides of that compartment. One side, the burn markings are lower than the other. So where'd the fire start? One side, you're going to look at the couch, you'll see full depth charring on the left-hand side and not full depth charring on the right-hand side. All these are indicators. So when that fire investigator comes out after the fact, you can look at this and you can put together where that fire started. Then you got to figure out the why, right? Was it intentionally set or not? If it's intentionally set, we may entertain the police department to help us because that becomes kind of a criminal act. If it's accidental in nature, typically the fire service is tasked with figuring out how it started and maybe offer up a way that it could be prevented in the future.